We're going to venture now into the Laplace transform. And the Laplace transform is something that we're going to use ultimately to solve differential equations. But first of all, I've got to introduce it to you. Now, a transform is transforms are something you've worked with for a while. You know, the differentiation is a transform. It takes one function and transforms it into another. Integration is a transform. For example, you take x squared and transform it into 1/3 x cubed, finding the antiderivative. And the Laplace transform is an example of an integral transform. When we talk about the Laplace transform, we're saying we're going to denote it this way. We've got capital L, a cursive L, f of t. That transform is defined this way. It's this improper integral, okay? E to the negative st times that function, that integral, that improper integral from 0 to infinity. And what we're doing is we're taking this function f of t and transforming it into another function, f, capital F of s, a function of s. So let me show you how this works. Let's suppose we want to transform 1. So we've got L and we've got a 1 in here, okay? So what we do is we just plug that in for the f of t. I plug in the 1, see, right there. And then I evaluate this integral. Now, we know how to evaluate improper integrals. It's going to involve taking the limit. I'm going to replace infinity with b and let b go to infinity. So we end up with this integral right here. Then we go through the process. Okay, the antiderivative of e to the negative s is negative 1 over s. See, I just take the e and divide by the derivative of the top. Okay, and now I've got the limit as b goes to infinity. Well, as b goes to infinity. Well, when I plug in a b in for the t, and I let b go to infinity, notice what happens. This thing goes to 0. Because the bottom is blowing up and the top is just staying constant. So the limit as b goes to infinity, this part right here, of course, this is just going to be 0. Minus when I plug in a 0 for t. When I plug in for a 0 for t, I get e to the 0, which is 1. And what it amounts to is I'm just left with this part right here. Okay, so I've got the top limit minus the bottom, and I just get 1 over s. So we say the Laplace transform of 1 is just 1 over s. So, congratulations. We have defined our first Laplace transform. And now I want to look at a couple more just to show you how the game is played. Let's suppose we want to find the Laplace transform of t to the 4th. This next one right here, t to the 4th. So I plug in and I've got this integral to evaluate. So now finding this transform is just a matter of using your integral chops. How good are you at integration? Well, this one right here is set up. It's just the way we would normally evaluate this integral is by parts and, doing parts over and over again, or we could use the shortcut and use tabular integration, which just is integration by parts, a shortcut to it. And remember how we do that. We take the one function, t to the 4th, and we start differentiating it. And we keep differentiating it until there's nothing left. So the derivative of t to the 4th is 4t cubed. Then we differentiate that, get 12t squared, differentiate that, 24t, and so forth. Okay? Then we take the other part, e to the negative st, and I start integrating that, finding the antiderivative. So it's going to be negative 1 over s, e to the negative st. I do the same thing with that one, get negative 1 over s squared. Then negative 1 over s cubed, 1 over s to the 4th, and negative 1 over s to the 5th. We've done this before. And then you set up, you draw your lines and do the alternating plus, minus, plus, minus, plus. And then your antiderivative is simply going to be this. I'm going to do the product of these. So this is going to be negative t to the fourth over s, see, times s to the negative, e to the negative st, that part. And then the next part is, now the minus on that one came from right here. This one comes from here, so I've got 4t cubed over s squared, e to the negative st, okay? And I keep doing that. And notice all these are coming out negative, okay? In this case, I have a plus here, but there's a minus here. So all of these come out to be negative. And as we go through here, we get our antiderivative, which is right here. And what I've got to do is evaluate this thing from 0 to b, where b is going to infinity. Now, when we plug in the b and let b go to infinity, all of these terms go to 0 because we're dividing by e to the st, or e to the sb, and b is going to infinity. So we've got this huge number on the bottom, and every one of these go to 0. Then we subtract off plugging in 0. Now when we plug in 0, this one goes to 0 because of the t. This one, and this one, and this one. The only one left standing is 24 over s to the fifth. See, when I just plug in a 0 for t, and I'm going to get this. I'm going to get, now remember, we're subtracting, so this minus becomes a plus, and what I get is, I get 24 over s to the fifth. 24 over s to the fifth. Now, one of the things you'll notice is that 24 is 4 factorial. Okay. And we've got 4 factorial over s to the fifth. Now, in general, when we find the Laplace transfer of t to the n, what that's going to give us is n factorial over s to the n plus 1. Yeah. So there's another Laplace transform that we found. Now I want to look at another one here where I've got the Laplace transform of sine kt. And as usual, we set up our integral. That's the easiest part. We just plug in here. And remember, we're going to use integration by parts here. Remember, integration by parts goes like this. You've got an integral of u dv, and you're going to find a u and a v, and your derivative is going to be, or your antiderivative is going to be uv minus the integral of v du. So you remember, in other words, I was just writing this formula up here just to refresh your memory. So what I have to do is find a u and a v and a du. So I'm going to do this. I'm going to let u be sine of kt. That means that du equals k cosine kt. And then dv is going to be the other part. dv is going to be this part. And that means v is negative 1 over s e to the negative st. So I go to work. I have uv, okay? Here is uv right there. See? Here's u, and here's v. So there's uv minus v du. Now, this minus and the minus in front of the integral of v du make a plus. So what I've got here is I've got v du, so that's going to be k over s, the integral, this integral right here. Okay. Now, I've got to do this process again because I've got nothing here. I still at this point don't have the integral of negative s e to the negative st sine kt. I've got another integral that is equally daunting. So what I've got to do is I've got to deal with this integral, which I've put in a nice blue rectangle here, and I do that work down here. And once again, I go through the integration by parts just like before. Okay, I'm going to let u be cosine kt, and then du is negative k sine kt dt, and I let dv be the same as before. Okay, so then I get uv minus the integral v du, and I get this thing. Okay, and I want to take that and plug it in here. Okay, so here's what I've got. Now notice I've dropped the bounds 0 to infinity because I'm just focusing on the antiderivative at this point. So I've got this, and here's this. This is what I had before. Okay. Okay. So here's what I've got. I've got this integral, got this, and then so that's this right here. Okay. And then k over s, I put in this new blue stuff here, this blue box. And then I go to work here with my algebra, clearing the parentheses. Okay, now I get this. Just clearing my parentheses. And you'll notice that I've got e to the negative st sine kt, and here I've got e to the negative st sine kt. So I think what I want to do is I want to add this term over here to the other side. And now, here's what I have on the left-hand side. I have the k squared over s squared, one of these, and the one of them, see? So, in other words, I've just rewritten it this way. And then I've still got what's on the other side. Now I add my fractions over here. I've got s squared over s squared. That's what 1 is. So I've got this times the integral. Now remember, I'm trying to solve for this integral. So I need to divide by its coefficient. So I divide by s squared plus k squared over s squared. Or in other words, multiply by the reciprocal, and I get this. Okay. Now I throw in those bounds, and I say, okay, I'm looking for 0 to infinity. Okay. And what I'm going to do is I'm going to, of course, evaluate this the way I normally would. I'm going to put a b in for t and let b go to infinity. Now, when I do that, notice what happens. This term goes to 0 and this term goes to 0. Because I'm putting a b in for t and letting it go to infinity. And once again, I've got this on the bottom and this on the bottom, and that makes for 0. Okay, now minus, now I'm plugging in a 0. Now when I plug in a 0 here, this goes away. Sine of 0 is 0. But the minus and this minus give me a plus. And when I put a 0 in for cosine, this is just 1. So what I've got here is I've got this times this. The s squareds cancel, and I just get k over s squared plus k squared. And this is the Laplace transform for sine of kt. So there's another transform. Now, part of the reason I did this was just to refresh your memory on how we can use integration by parts. But anyway, now sometimes you'll see a piecewise function like this one. And how do we deal with the Laplace transform here? Well, you break it up. In other words, I've got this. I'm going to take this piecewise continuous function, and I'm going to do take the first part, okay, this negative 2 from 0 to 1. Okay, I'm going to take care of that integral, and then I'm going to put the 2 in and go from 1 to infinity. So I'm breaking up this integral. But I go through that integration, and what I eventually get is this result right here. And you can go through, this is not an integral that you'll have trouble with. Now, what I want to point out just in conclusion here, is when you go through here and work through these, finding the Laplace transform, remember this is a linear transform. And what that means is, if you have something like this, if you want to find this Laplace transform of alpha f of t plus beta g of t, you can rewrite that this way. You can rewrite it as a sum of the two transforms, and you can factor out that constant. And why can you do that? Well, because it's just integration. So dig this. Here is the Laplace transform. See, I just put in place of the function, I put alpha f of t, beta g of t. And then I split up the integral as I'm allowed to do with integration. And then I factored out the constant. Factored out the constant there. Factored out the constant there. And notice what you get here is this is just alpha. Whoops. This is just alpha L of f of t. And this is beta L of g of t. See? So this Laplace transform is a linear transform. So that's something that will make things easier for you when you're working through some of these problems.